So here's one of the MyMathlab problems, and throwing caution to the wind here, and I don't know if I really needed to expand the graph that much, but I suppose this is fine. We want to indicate the intervals where it is increasing. It may also ask us the intervals where it's decreasing and the intervals where it's constant. And I don't want to include the endpoints. If we generalize the definition of increasing, decreasing, or constant a little bit more, there are certain situations where it is permissible to include the endpoints, but just for simplicity. To make our lives less complicated, let's not include the endpoints, and I think this will be fine. So there's that, and I should probably also indicate the instructions. Where'd they go? On what intervals is it increasing? Now, that's fine. It covered up the graph a little bit, but I think we see the key features of it. Now, on the test, there won't be multiple choice, so let's try to handle this in the absence of any of the possible answers there. As we look and see where is the graph rising, I'm thinking right there, the graph is going up as we go from left to right. And also right there, those are the two portions of the graph that I see where it's rising as we go from left to right. Now let's take and consider what's the portion of the x-axis where that's happening. We're just interested in the x-coordinates of these points, not their y-coordinates. And I'm going to leave off the endpoints. So it starts happening right there. Does that look like -6 to you? X equals -6. I think that's the x-coordinate of that point. If we had to label that point, it would be the point -6, -4, something like that. And the coordinates of this point would be +2, +4. So I'm thinking the graph starts increasing at x equals -6 and stops increasing at x equals 2. So I'm going to say f is increasing on the interval from -6 to 2. Notice the y coordinates of those points do not get mentioned. They're there, and it is important that the y coordinate of the point on the left is lower than the y coordinate of the point on the right, otherwise it wouldn't be increasing. But we don't mention the y coordinates, just the x coordinates. It's also increasing. This other portion of the graph that I've shaded in red, it looks like it starts, what is that point there? 1, 2, 3, 4, 5, 6. That's the point 7, -3. And that's the point, where is it? 6, -3. 1, 2, 3, 4, 5, 6. That's a 6 there. And the y coordinate is 9. 1, 2, 3, 4, 5, 6. So it looks like it stops increasing at 2, and then it's undefined between 2 and 3, and then it resumes at 3. It's decreasing until we get to 6, and then at 6 it starts increasing again. So I'm going to say it's increasing on the interval from 6 to 9. So there are two portions of the x-axis where it's increasing. It's increasing on the interval from -6 to 2, and then it's increasing on the interval from +6 to +9. There we go. So those are the intervals where it's increasing. Where is it decreasing? I'm sure it's going to ask us this, so I'll go ahead and answer it. F is decreasing on, well, let's see, just the one interval, right? Just, if I want to shade the portion of the graph where that's happening, that's the portion of the graph where the graph is falling. It starts falling at x equals 3, it looks like, and it continues to fall until x equals 6. So could we say it's decreasing on the interval from 3 to 6? Let's see, what if I could, well, So I wanted to select that. Come on. You won't let me do that. On the interval from 3 to 6, and f is constant. I'll go back to red there. F is constant. We just look for a portion of the graph where it's a horizontal line segment, and I'm thinking it's right there. So from -8 to -6, that's where the graph is. That's where the graph is constant. Now go back to MyMathlab and just make sure that's the sort of thing they're looking for. It's multiple choice, so it should be easy enough to figure that out. What intervals is the function increasing? I think we said it was increasing on the interval from -6 to 2 and 6 to 9. We'll check that. And on what interval is the function decreasing? Okay, so we have to input the coordinates. It's decreasing. The x-coordinate is 3 where that starts. The x-coordinate is 6 where it stops decreasing. And then constant. The x-coordinate is -8. And then the y-coordinate is -6 where it stops being constant and kind of jumps downward and begins to increase from there. Notice in each case, it's just parentheses on either side. So we're omitting the endpoints. In some cases, it wouldn't be wrong to include them. In other cases, it would be wrong to include them. So rather than having to deal with those cases, we're just going to omit the endpoints when we're answering the question, is it increasing, decreasing, or constant? If it'll give me another one of these, would it be one more? It may not. Determine the intervals on which the function is increasing, decreasing, and constant. So where is it increasing? If I wanted to indicate the portions of the graph where the graph appears to be rising, I'd certainly include that, and I would include that, but I think since the arrow is kind of pointing down and to the left, the indication is it's going to keep going down and to the left forever and ever and ever. So the idea is it's coming up from here. So if we were to go to the left, the graph would be going down, down, down. So as it's coming from the left, it's going up, 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 up until it gets to that point. Looks like -7 right there where it stops increasing. So I would say f is increasing on the interval from -infinity to -7. Oh, and also on the interval, you could use the word and. The word and in this context doesn't mean intersection. It simply means this one and also this one. You could separate these with commas. I don't think union is appropriate, and I don't think MyMathlab is really going to give you the opportunity to use the union symbol. Hope not. You really don't want to say that a function is increasing on the union of two intervals, because it could be increasing on one and then jump way down to the next one, and then be increasing on that one without being increasing on the union of the two intervals. So I'm just going to use a comma there. Looks like from -2 to -1. It's increasing. Again, not mentioning the y-coordinates. When we indicate where is it increasing, where is it decreasing, it's an interval in the domain, and it's only the x-coordinates that come into play. So as far as how MyMathlab would have us enter this, list them, it does say use a comma to separate answers as needed. So negative, and how do I, /infinity, /INF? Ooh, no, I didn't want that. There's a shortcut. Did I do backslash? once again, I want to do that shortcut. It's front slash INF if I don't want to type. Okay, there it is. Comma -7, close the parentheses, and then comma, also increasing on the interval from -2 to -1. Let's see if it likes it. List the intervals on which the function is decreasing. Where is it decreasing? Well, it stops increasing at -7 and begins to decrease until the x-coordinate is -5. From -7 to x equals -5, from there to there, and I believe that's the only interval. Is that the only interval where the function's decreasing? So from -7 to -5 is what we're looking at there. And will it ask us where it's constant? It will. List the interval or intervals on which the function is constant. So it stops decreasing at -1. Sorry, it was increasing from -2 to -1, stops increasing at -1, and then goes straight across forever. The arrow indicates it continues infinitely far in the direction that it's pointing. It's not pointing up or down, it's pointing straight across. So I'm thinking from -1 to positive infinity, f is constant on the interval from -1 to positive infinity. And let me go ahead and fill in the other one, just for reference here. Decreasing, we said, on the interval from -7 to -5. Let's try, let's just verify this with MyMathlab, see if it's good with it. -1, again with the front slash INF, close the parentheses. And I missed it. Why did I miss it? Was there an... Oh, yes, indeed. That's why I missed it. Yeah, we all got to include from -5. Okay. To -2. It's increasing on that one as well. So, you think it'll be okay if I don't put them in order from left to right? Did it say put them in order from left to right? Let's find out. Let's get 3 chances. So here's chance number 2. -5 to -2. Check it. It liked it. Okay, good deal. Oh, thank you. I don't know how I missed that one. But miss it I did. Determine the domain and range of the given, well, domain and range of the function given the graph of the function. That's how I would phrase this problem. To determine the domain of a function given the graph, we ask ourselves questions like how far to the left does the graph go? How far to the right does the graph go for the domain? Because the domain is the set of all x coordinates of points on the graph. So it's the portion of the x-axis occupied by the graph. So I'm looking for the domain. I'm looking to see it goes as far to the left. I'm going to say it's -7. Now, critical difference between how we express whether a function's increasing or where a function's increasing and where a function's decreasing, and the domain and range. Our lives are simpler when we're expressing an interval where it's increasing or decreasing. By default, we just make them all open intervals. We don't worry about the endpoints, only parentheses. For domain and range, it's kind of a big deal whether -7 is in the domain or not. If there's a solid dot at that point that has -7 as its x-coordinate, and it is the point -7, -3. I'm thinking there's a solid dot there. That means -7. That means, number one, that point is on the graph. It's a member of the function. So negative 7 is in the domain of the function, and negative 3 is in the range of the function. So when we write the interval to describe the domain, we want to make sure to use a bracket for that negative 7. And as we go work our way to the right, there are no gaps. The graph is continuous as we go all the way from the left to the right, and it does stop at positive 7 at a solid dot, which means the ordered pair 7, 1 is a member of the function, which means that 7 is in the range. 7 is in the domain and 1 is in the range, but I guess 1 is not at the endpoint of the range, so it's not as big a deal with the range. So here goes. The domain of the function f is the closed interval from negative 7 to 7. That's the domain of this function. It's the portion of the x-axis that the graph occupies. For the range, we ask ourselves questions like, how low does the graph go? How high does the graph go? The range is the portion of the y-axis that the graph occupies. What is the y-coordinate of the lowest point on the graph? It's going to be negative 3. Negative 3, we said, is in the range because the point negative 7, negative 3 is on the graph, and that's the lowest point on the graph, so negative 3 is the least number in the range. There are several different points that could be considered as the highest points on the graph. Basically, all the points on this little line segment right there are the highest points on the graph, and they all have positive 3 as their y-coordinate. So the range extends from negative 3 to positive 3, including both negative 3 and positive 3. So domain, closed interval from negative 7 to 7. Range is the closed interval from negative 3 to 3. I'll just ask, did I get this right or did I miss it? I'll trust you, and we won't take the time to consult MyMathlab with every single one of these.
I just put it into it.
It didn't like it. Okay. All right. I should check it then. I can't imagine what was there not to like. Negative 7. I don't know. Was it negative 8? Did I read it wrong? The domain is negative 7 to 7. So let's check that. That one's good. Did you do them separately or all at once? Maybe if you did them all at once, it wouldn't have liked having both those intervals input as the domain. So it goes as low as negative 3 and as high as positive 3, and it looks like it catches everything in between. So we'll check that one. And so that one's good. So did MyMathlab give you a different problem for a different graph, different picture?
I think so. It was like really similar.
Yeah, maybe they just translated up or down or left to right, something like that for a little variety. That could be what it was. Next one has a little bit more going on. There's some gaps in the graph. Let's see if we can determine what it wants here. Again, the question is determine the domain and range of the given function by considering its graph. So here goes. How far to the left does the graph go? The point negative 6, 3 is a solid dot. That means it's on the graph. That means negative 6, 3 is a member of this function. So negative 6 is in the domain. I'm thinking that's the least number in the domain, the farthest to the left. So negative 6 is the least number in the domain. I could ask how far to the right does the graph go, but there are going to be some gaps in the middle. So maybe we should just work our way from left to right and see when those gaps appear. The first gap occurs at -3. There's, in calculus, we call this a jump discontinuity. The graph is it's going along its merry way like this, and all of a sudden it jumps and ends up way down there. So it's a discontinuity in the graph. But I don't think there are any x coordinates that get left out, because we're going along. It's everything between -6 and -3. Now we've got an open circle here, which means if that's all we had, -3 would not be in the domain. So we don't get -3 in the domain from that portion of the graph. But when we jump down to that other portion of the graph and consider that point down there, that is the point -3. When there are too many copies of -3. It's the x-coordinate -3 that's important here, because that point with an x-coordinate -3 is on the graph. That means that -3 is in the domain. So we really haven't left anything out yet. So we keep working across all the way over to this point right there. That's got an x-coordinate of 1. Sorry, -1. So it looks like the domain includes everything from -6 all the way over to +1 without leaving anything out, even though there was a big jump, discontinuity in the graph. So I would begin by saying the domain of f, now I'm going to say is, but this is not going to be the entire domain. It includes the closed interval from -6 to -1, and then there's some more. If we're wondering whether or not 0 is in the domain, it's not. There's no point on the graph that has 0 as its y-coordinate, and 0 is not all that's missing. Numbers like 1/2 and -1/2, numbers like 0.9 and -0.99999 fail to be in the domain. Nothing between -1 and 1 appears to be in the domain. Domain picks up again with x equals 1. So we've got this portion of the domain from -6 to -1, and then there's nothing between -1 and +1. It picks up again with +1, and then from 1 over to 4. And then it stops at that point 4, 7. Solid dot, so 4 is in the domain. Everything between 1 and 4 is in the domain. So put a comma, and then 1 to 4. That's the domain. Now that's sufficiently complicated where I'd like to see if MyMathlab agrees with us. So the domain is, oh my goodness. Yeah, it's okay to write union. In fact, it's appropriate to write union here. Increasing and decreasing, we run into problems because you want to consider each individual interval one at a time. But when you consider the domain, it's the set of all x values, so it makes sense to write separate intervals and join them together with the operation of union. So I'll go ahead and put that in the notes there. That's the domain of this function. It's the union of these two intervals. And it's going to be closed interval, -6 to -1, union, closed interval, +1 to 4. What's the range? How low does the graph go? What is the y-coordinate of the lowest point on this graph? Well, I think it's -3. It goes as low as -3. It's a solid dot, meaning that -3 is in the range. And let's see if there are any gaps as we work our way upward. If we're wondering, is -2 in the range? The answer is yes, because we could go over to the left, and there's a point on the graph with an x-coordinate of -2. If we're wondering, let's just keep working our way up, 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 up. Is +2 in the range? The answer is yes, because we could either work our way to the left and find a point on that little piece of the graph that has a y-coordinate of 2, or we could go over here and find a point that has a y-coordinate of 2. So for either reason, 2 is in the range. So we keep on working our way up. Goodness, there are a lot of numbers, a lot of points on the graph, rather, that have a y-coordinate of 3. There's that one right there, there's that one right there, and it's all of those have y-coordinates of 3. So we keep on working our way up. I haven't found any gaps. Do you see any number between -3 and +7 that's not in the range? I don't think so. I think anywhere between -3 and 7, if we stop and look to the left and look to the right, and in some cases both directions, we find at least one point that has that number as its y-coordinate. So each of these numbers from -3 to +7 is in the range. Hoping to be able to skip one of these in a little bit. We'll see if this is a similar problem. It is. It's got an interval that it looks like a variation of that problem we looked at a moment ago, asking for the domain and range. Let's move on. There's other things we have to talk about. I would like to do that one, but let's move on. Okay. Let's go back to the notes for the definition of relative minimum and relative maximum points and relative extrema, extreme values. I'll draw some pictures that go with these, hopefully to give a decent idea of what we're talking about here. Go. Here's my picture. I'm going to use the letter A for relative maximum, and I'm going to use the letter B for relative minimum, so I don't have to draw two different pictures. I think one will be sufficient. So imagine a graph that looks something like this, typical of maybe a third-degree polynomial function. And consider this point right here that looks like it's maybe not the highest point on the graph, but it's a point at the top of a hill. It's as high as anything close by. I'm going to say its x-coordinate is A, so the point is A, comma, f of A. I'm going to call that a relative maximum point. Relative maximum point. And the reason we can call it that is because it's at the top of a hill. That means there exists an interval, specifically an open interval, so that it contains A and a little bit to the left of A and a little bit to the right of A, where f of A is the maximum value of that interval. That is, f of A is greater than or equal to f of x for everything in that little interval. And that's a highly technical way of saying it's at the top of a hill on the graph. So it's a relative maximum point. I'm going to use B for the relative minimum, so I don't have to draw a new picture. Let's say this is the point B, f of B. I'm going to say this is a relative minimum point, and it's a relative minimum point if there exists an open interval containing B such that f of B is the lowest value in that interval. It's at the bottom of a valley. If we look at the graph, and if we pick any other x in there, f of B is going to be greater than or equal to f of x. These points typically occur where a function stops increasing and starts decreasing, or where it stops decreasing and starts increasing, and they help us to determine the intervals where a function's increasing or decreasing. Likewise, if we happen to know the intervals where a function's increasing or decreasing, they help us to determine where these relative extreme points lie. The y-coordinates of these points are called relative extreme values. So f of a is called a relative maximum value. To do that, f of a is a relative maximum value which we say occurs at x equals a. F of b is a relative minimum value which occurs at x equals b. Let's look at some of the MyMathlab problems, and then I want to make sure to include at least one of the problems from the lecture notes, unless MyMathlab has one that will suffice. Determine any relative maxima or minima of the function and the intervals on which the function is increasing or decreasing. We've done increasing and decreasing. I think we've done enough of that. So let's just see if we can find the relative extreme points here. Does the function have a relative maximum or minimum? If I ask that as an open response question on the test, if it has one, I suppose you could say yes, but I would want you to be more specific. If it has a relative maximum, indicate that. If it has a relative minimum, indicate that. In this case, it's a point at the top of a hill. So we will say it has a relative maximum. The relative maximum, so it asks for the x value first, and then it indicates that it asks for the actual value, which is the y-coordinate, second. So it occurs at x equals, and I'm just looking at the picture here, it looks like 2.5 is the x-coordinate at that point at the top of the hill, and the y-coordinate is 3.25. I'm thinking that's what it wants. So it's a relative maximum value of 3.25, which occurs at x equals 2.5. And then it's going to ask where is it increasing, where is it decreasing, but I'm going to go ahead and move on. A little bit more of this. I think it's easy enough to know what it's asking for there. I don't think we need to take our time with that. Graph the function. It's going to be a parabola. That shouldn't be too much trouble. Estimate. I'm curious how the graph is going to work, though. Choose a tool from the palette. So f of x equals 5 minus the absolute value of x if x equals 0, what is f of 0? What's f of 0? It's 5. 5 minus 0 equals 5. So if we're plotting points, we'd plot the point 0, 5. If we scoot over a little bit to the right, absolute value of 2 is 2. So 5 minus 2 is 3. We plot the point 2, 3. If we scoot a little bit to the left, thing to observe here is that if you put in a positive value for x and the corresponding negative value for x, it's opposite because you're taking absolute value, you get the same answer in both cases. So the absolute value of -2 is also 2, so we get 5 minus 2 again, which is again 3. So we'll talk more about symmetry in an upcoming section, but it can be shown here that this graph is symmetric with respect to the y-axis. It's kind of like a rooftop. That's what the shape looks like. It goes through the point 0, 5, and then 2, 3 is there, and -2, 3 is there, and it looks like that, and I think 5, 0 is another point, and -5, 0 is another point, and so this is the graph. So choose a tool in the palette and follow the instructions to create your graph. Oh, it must be the V-shaped tool. Are you thinking this is the V-shaped tool? It's an upside down one. But let's use the V-shaped tool and follow the instructions. Here goes. Click the graph to plot the vertex. Well, I'm going to try to click it right on 0, 5. Maybe close enough. Ooh. Click the graph to plot another point. How about 5, 0? That was easy. I like the V-shaped graph plotting tool. I'm pretty sure this is it. I'm going to save it. And do we want to check it? So it's happy enough with that. Good. Determine on which intervals f of x is increasing. Okay, sure. It's increasing on an interval. What interval is it increasing on? The graph is rising, and there's no arrow down there, but the idea is it continues down to the left, all the way infinitely far down to the left. So negative infinity. Mm-hmm. Yeah. So negative infinity to, and it doesn't stop until it gets to a point. It doesn't stop increasing until it gets to a point with what x coordinate? It keeps on and on until that point at the top. What's the x coordinate at that point in the top? So 0. And again, always parenthesis when we're indicating increasing or decreasing of intervals, just because it's simpler that way. Check the answer. Good. And it's going to ask us, where is it decreasing? I guess. Continue. The function f is decreasing, so it starts decreasing at 0, and it continues to fall forever. As far as we go to the right, it continues to decrease. So check it. And once we get the green light, we will continue. So we want to know, determine the relative maxima. Select the correct choice below, and if necessary, fill in the answer box to complete your choice. It does have a relative maximum, and the maximum value is the y coordinate of the highest point. And the highest point is 0, 5. The y coordinate of that point is 5. The x coordinate of that point is 0. So it has a maximum value of 5 at x equals 0. Does it have a relative minimum? Point at the bottom of a valley? No. No. There is no point at the bottom of a valley on this graph, so I'm just going to say it doesn't have one. Good. All right, making some progress here. Problem 10. It's another parabola. I'll let you use the parabola graphing tool and do that one. Third degree polynomial function. Let's see if we can get a decent graph of this one on the graphing calculator. If you wanted to plot a bunch of points, you could do this with a conventional calculator, but it's much faster on a graphing calculator. And there'll be an example, probably on the next test, where the x coordinates of these points at the bottom of the valleys and the tops of the hills will not be nice. So you'll need the graphing calculator to find the coordinates of those points. So let's look at this one. Here we go. Y equals start with the negative sign. The calculator will give you a syntax error if you start with a minus, so be sure and start with the negative to lead the expression. X to the power of 3. Move off the exponent if you need to. Plus 6x to the second power minus 9x minus 2. Negative x cubed plus 6x squared minus 9x minus 2. And is that the window that it's giving us? The viewing rectangle, negative 3 to 7, negative 20 to 15. Ordinarily, we kind of have to figure this out on our own, but MyMathlab is going to go ahead and tell us. I might as well take advantage of that. Negative 3 for the x-min, 7 for the x-max. I'm going to leave the x scale at 1 because that would give us about 10 tick marks between negative 3 and 7. Negative 20 for the y-min, and 15 for the y-max. And I think that's just asking for a y scale of 5. If we go with the y scale of 1, that's going to be 35 tick marks, and it'll clutter the x-axis up. We don't want that. But an x scale of 5, I think, would be, it would clutter the y-axis up, and we don't want that. A y scale of 5 is much better. That would just give us maybe 5 or 6 tick marks. Let's press the graph button and see what it looks like. Does your graph look something like this? Something like this. Anybody get a syntax error? No syntax error? Anybody get an invalid dimension or dimension mismatch error? Okay. Key points that we're looking for, points at the bottom of the valley. And I think this has been designed so that the x-coordinate of that point is 1. We'll look at a technique in the moment where we can use the calculator to find a really good approximation for the coordinates of that point. If it's not nice, I think it's nice though, I think it's negative 1. Sorry, positive 1. And I think this one, the x-coordinate is positive 3. So I think the x-coordinates of those points are nice. Based on that, find the intervals on which the function is increasing. There's just one interval where I see this function's increasing. It looks like it's decreasing all the way from negative infinity, and it gets to x equals 1 and stops increasing. Stops decreasing and starts increasing. So x equals 1, and then it increases until it gets to x equals 3. So I believe it's increasing on the interval from 1 to 3. The intervals where it's decreasing, maybe not a bad idea for me to capture this and write on it. Just want a scroll bar. That's so much to ask for, just a scroll bar. Going to give it to me. Okay, add a new page. So on the interval from 1 to 3, the function is increasing. It's decreasing on the interval from negative infinity to 1, and on the interval from 3 to positive infinity. Find any relative maxima. I believe we're going to need to know not just the x-coordinates of these points, but the y-coordinates as well. If we know the x-coordinate, we can simply evaluate the function to determine the y-coordinate. Second, calculate. That's on the trace button. If you press the second button and then follow that with the trace button, it'll give you the calculate menu. If you know for sure that the x-coordinate of that point, and we want a relative maximum, so the point at the top of the hill, that would have had an x-coordinate of 3, would it not? Was that the one with an x-coordinate of 3? I'm looking for the the y-coordinate of that point right there, 3 comma something. So let's evaluate the function at 3. So number 1 on the list, second calc 1. Let's input 3 and see if it tells us that the y-coordinate is -2. So the relative maximum value is -2. It occurs at x equals 3. No doubt it'll ask us for the relative minimum. The relative minimum occurs at x equals 1. If we evaluate this function, is it going to let me type in the 1? I guess it's not. If we evaluate this function at 1, I'm just going to type 1 and enter. Point 1, -6 is on the graph. So the relative minimum of -6, which occurs at x equals 1. Okay. See if I can move things along a little bit, and it should give us a chance to use the relative minimum and relative maximum features on the calculator, but there are a few application problems here. We actually have to look at a geometric figure and express some quantity as a function of x. And this is an example of one. Yard-bird landscaping has 46 meters of fencing with which to enclose a rectangular garden. Is that where the calculator was? Oh, good. With which to enclose a rectangular garden. If the garden is x meters long, express the garden's area as a function of the length. So here's our rectangular garden. And there's a total of 46 meters of fencing. And so the 46, certainly we've got to fence it on these two sides, left and right. We got to fence it on that side and that side. I guess the top view, you could say left and right, or if you're standing in front of it, the side away from you, the side toward you. This rectangle has 4 sides. And all 46 meters of the fencing has to be enclosed. Now the garden is x meters long. X meters long. So if the length is x, both of those sides are going to have x meters of fencing along them. Can we express the entire perimeter, basically, of the rectangle as a function, well, the perimeter is 46. Can we express the other two sides as a function of x? And if we can get the other two sides as a function of x, then we can express the area as a function of x. It might be helpful to call them y first, and then see if we can express them in terms of x. Call them y, because you know that the perimeter is going to be 2 times the length plus 2 times the width, and that's going to add up to 46 meters. So with this equation, if you solve this equation for y, you can express y as a function of x. So I'm going to subtract 2x from both sides. 2y equals -2x plus 46. If we divide both sides by 2 here, there's my scroll bar. Y equals -x plus 23. So for example, how long might we want this rectangular garden to be? Could it be 20 feet long? It'd be kind of skinny if it was 20 feet long, but we might want it to be 20 feet long. We might not want it to be all that wide. Who needs a really wide garden? What if the garden is 20 feet long? X equals 20, for example. How much fence do we have left after we put 20 meters on one side and 20 meters on the other? If we start with a total of 46 meters of fencing, how much is left? We had 46 meters and we used 40 of them. So we've got 6 left. But we still have 2 sides we have to fence. So I guess we can go with 3 meters on each side. So we make that 3 and that 3. That would be one example. But that's our calculation. See, if we input a 20 right there, negative 20 plus 23, that tells us how wide it can be. That tells us how wide it can be. So y, in this specific case, x is 20, y equals 3. In general, x is x, and y is negative x plus 23, which tells us we better not make it longer than 23 meters. Because if we do, the width is going to be negative, and we can't have that. So it's got to be less than 23 meters when we decide how long it's going to be. So the length is x, and the width is negative x plus 23. So the area, which is length times width, I do not know why I chose to write this in cursive, but it didn't go that badly. Cursive is not my thing. Length times width, it's going to be x times negative x plus 23. And if we simplify that, I'm thinking MyMathlab might want us to simplify that. It's going to be negative x squared plus 23x. So if we wanted to calculate the area of this 3 by 20 rectangle, this function would do that for us. It's actually a function of x. Let me look at that MyMathlab problem again, make sure I'm following all the directions here. Which of the following expresses the area of the garden as a function of length? This looks like it has the x term first, followed by the x squared term. So it might help us to compare these if I reorder them and write it 23x minus x squared. Does that help? It does. It's the last one. 23x minus x squared. That is what we're looking for there. Three minutes and change. I think we can do this one. A summer camp. Actually, there's no way we'll finish this one, but I'm going to start it anyway. A summer camp has 160 feet of float line with which to rope off 3 adjacent rectangular areas of a lake for swimming lessons, one for each of 3 levels of swimming ability. Wow. A beach forms one side of the swimming areas, so maybe we don't have to rope that off. Suppose that the width of each area is x feet. Answer parts A through C. Express the total area of the 3 swimming areas as a function of x. Let's see if we can get that much done before we have to go. Total area of the 3 swimming areas as a function of x. Well, I'm going to take that side that has to have rope, this outside side right here, and call that y. This other side doesn't have to have rope, So I'm not going to give that a dimension. We can ignore that. But I believe x plus x plus x plus x plus y equals 160 feet. Does that make sense? That's where we have to have rope. Want to be able to express y in terms of x, so we can express the area in terms of x, because the area equals x times y. So 4x plus y equals 160. Y equals 160 minus 4x. So the area, and you can write it as a function of x, is going to be x times 160 minus 4x. I think it is helpful in each case to use that y, that extra letter of the alphabet, for that extra dimension of the rectangle. If you just kind of stare it down and try to come up with the 160 minus 4x, I think the problem's going to be maybe a little bit too complicated. So x times 160 minus 4x, or MyMathlab might want us to simplify it, 160x minus 4x squared, like in the previous example. Let's find out. I'm going to try 160x minus 4x squared. Is it going to like it? What do you think? Will it like it or not? Let's find out. It liked it. It might also have liked it in factored form. I don't know. We have less than a minute. What's the next question? Find the domain. Now the domain, in general, the domain of a function like this would be all real numbers. But x represents how wide, how far into the lake we can go. So I don't think it's a set of all real numbers. I think if x is greater than a fourth of 160, it's going to be too much. If x is 40 or more feet, then our dimension of y is going to be nothing. So I think it's got to be less than 40, and I think it's got to be at least 0. And MyMathlab might not like this, but I think it's from 0 to 40. If we go more than 40 feet, we're not going to have enough rope to close it off and get that other dimension. So I'm going to check it and see if MyMathlab, 0 to 40. So something to think about, the physical constraint of the situation. Our time is up. Thanks so much. I will shut this off, and I will see you next time. So in the MyMathlab homework, we're looking at the problem where there's some rope that's going to be used to enclose three rectangular swimming areas. It's going to be an X by, not quite sure how long it's going to be, but if we measure from the edge of the lake, the shore, basically, out as far as we're going to go, that's a length of X feet. And the other dimension, which is going to cover all four of these, that I'm calling Y right there. It goes from there all the way over to there. That gives us the other dimension of that rectangle. Are the displays not on? Let's try that again. How about that? Better. Sorry. That's the other dimension. So we did this last time and came up with the area, of course, is length times width, so it's x times y. The area then will be this dimension, x, multiplied by 160 minus 4x. We were able to come up with that by observing that if we take the four lengths of rope, each x feet long, and the one at the back end of the swimming area that's y feet long, and add those up, that's our 160 feet of rope. So those four x's plus the y equals 160 feet. If we solve that equation for y, we get y equals 160 minus 4x. And just as a for example, suppose we want to let x equal 20 and let it be 20 feet from the shore to the end of the swimming area. That would be 20 right there. We could just kind of stare this down and figure out how long the three combined swimming areas could be, because we've got 20 feet of rope and 20 feet of rope and 20 feet of rope and 20 feet of rope. That's a total of 80 feet of rope, and that leaves us with 80 feet of rope out of the 160 that we have, so it could be 80 feet long. In that case, that gives us the other dimension. Now that number 80 could also be calculated by substituting 20 right there. 4 times 20 equals 80, and 160 minus 80 equals 80. So we've effectively expressed the length of the combined swimming area in terms of the width. So we've got both dimensions written in terms of x, and once we have that, we can express the area in terms of x. The length times the width, x times the 160 minus 4x, and that gives us this function. You can simplify it if you want to. MyMathlab might want that, 160x minus 4x squared. In fact, I think we actually input 160x minus 4x squared last time, and it liked it, if my memory serves me correctly. Maybe I'm just making that up, I'm not sure. But I think MyMathlab actually liked that. That's the A part. Now the B part asks us for the domain. What is the domain of this function A of x? We encountered that right at the end of class, and I tried to wave my hands at it to indicate an answer. Here's the considerations that we need to make. If I just wrote this function down, I just gave you this function, A of x equals 160x minus 4x squared. Didn't tell you what x represented, didn't tell you what A represented. As far as we knew, there are no physical constraints on the variable x or the variable A. They could be positive, they could be negative. The domain would be all real numbers, negative infinity to positive infinity. But the fact of the matter is, x is limited. We only have so many feet of rope, and the area is limited. There's only so much area we could possibly enclose. The lake is only so big, I'm thinking. But the constraint is going to be in the amount of rope that we have. I'm assuming the lake is plenty big for as large or as long as a swimming area as we want. So let's think about this. However wide or deep the swimming area is going to be, it's going to be x feet. We have to have 4 of those. And 20 is fine. 20 feet, there was plenty. We went 20, 20, 20, 20, and there was plenty of rope left over, so it could be reasonably long. But if we'd made it longer, say 30, 30, 30, 30, that's 120 feet of rope that's used, and we would have how much left? 40, 160 minus 20, 160 minus 120 is 40. So it could be 10 feet deeper, but it would only be half as long in that case. Well, that's fine if we don't mind the swimming areas being a little bit skinnier. But what if we pressed it farther? What if we made it 35, 35, 35, 35? 35 times 4 is about 140, I think. Then it can only be 20 feet wide in that case, or 20 feet long, I suppose, and that's divided by 3, so the swimming areas are getting quite skinny. You can maybe do laps back and forth, but not a whole lot else. What if we pressed it to 40? And I think I mentioned that at the end of class last time. What if we made it 40 feet, 40 feet, 40 feet, 40 feet? How long is it going to be? Well, we have 160 feet of rope, and we've used 40, 40, 40, 40. That's all our rope. So there's no rope at the back side of it. So it can't go as it can't go as long as 40 in that case. So if I'm thinking of the domain of the function, the x values, I can go all the way up to 40. If I don't mind it being really, really skinny, I could go 39 and a half, 39 and a half, 39 and 39 and a half, but I can't go out to 40. Then I don't have any rope at all for the backside enclosure. And the other consideration is x which is the width of the swimming area, needs to be positive. It wouldn't make sense for it to be 0 and just have 160 feet of rope there lying there on the shore and 0 feet of swimming. That makes no sense. So I'm going to say 0 to 40. Now within this, there's some other values of x that, while technically they give us 3 enclosed rectangles, they wouldn't be big enough to swim in, or it just wouldn't make sense. So so you could even shrink this a little bit more if you wanted to use some common sense when you sit down and start planning this. There's no way 1 feet, x equals 1 or x equals 2 or x equals 38 or 39. They're not going to make sense either. But I'm pretty sure MyMathlab's going to be okay with 0 to 40. Can't be 0, can't be 40, but anything in between, and we're actually going to have positive area for each of these swimming enclosures. So that's the B part. The C part wants to find the value of x that gives the maximum total area in which to swim. And I think the first matter that we should address here is, why wouldn't all values of x, whatever value of x that we choose, however shape we want to make this thing, why wouldn't they all give the same area? And unless we're convinced that, yeah, if we change the value of x, it's probably going to change the value of the area, total area, there's no point in answering the question. So let's see if we can convince ourselves of that. Suppose we make it, let's see, careful. Suppose we make it like this, where x equals, I'm not sure how close to scale this is going to be, but let's say 25, 25, 25, 25, and 25. That's 100 feet of rope. And we have a total of 160, so that leaves us with 60. So if we make it 25 by 60, then the total swimming area, that'd be one way to do it. How much area would that enclose? Area equals, we could calculate this 2 different ways. We could take a 25 and put it right there for x, and a 25 and put it right there for x, and evaluate that function, and that would give it to us. Or we could just say 25 feet times 60 feet, oops, and that would be the dimensions of this, so that gives us the area. 25 times 60, I want to say is, I think it's 1, 5, 0, and maybe another 0. 1,500 square feet. Okay, so if we do it like this, it would enclose 1,500 square feet, and maybe that's just fine. Maybe that's just fine. It's good. We've got plenty of elbow room in there. Each enclosure, a third of 60 is 20, so each one would be 25 by 20. Maybe that's a good way to do it. What if, though, we decide to make it a little bit deeper, go deeper out into the lake? And there might be some other considerations as far as the depth of the lake. I mean, that's probably something that we should think about, but that's not something we're considering here. We won't be able to make it as long. Each enclosure is going to be skinnier, maybe only that long, and maybe the scale isn't quite right. I still want to use 160 feet of rope, but I'm going to go 30, 30, 30, 30, and that's 120. So we have 40 feet left, and I don't think I've scaled this quite right. 40 would be 2/3 of 60, and I don't think I've shrunk it by a factor of 2/3. Didn't shrink it quite enough. But I believe those would be the dimensions, right? Is that a total of 160 feet of rope? Yeah. The area here is a little bit easier to calculate. If we make it 30 feet by 40 feet, 30 times 40, it's only 1,200 square feet. So we're choosing different dimensions, although we're using the same amount of rope. If we make it wider, then less area is enclosed. We could go 35 feet and see what that does. We could back it up to 20 or 15 or 10 or 5 feet and see what that does. But somewhere in between, maybe, well, somewhere in between 0 and 40, maybe, I'm thinking there's a value of x that makes this area as great as possible. So what I want to do is graph this function using the graphing calculator, see if we can find a decent viewing window for it. I think MyMathlab actually provides you with a kind of a makeshift graph for this. But let's do this on the graphing calculator and see if we can find the maximum value of this function. So function we're graphing is that one. I'm going to clear this out, and I'm going to graph, I'm going to press the y equals button, clear whatever's there, and type 160x minus 4x to the second power. What's going to be challenging about this is finding an appropriate viewing window. I don't know what viewing window I have right now. This is not going to be an appropriate viewing window. Even if I were to zoom 6, that would not be an appropriate viewing window. Zoom 6, I might see just a little snippet of the graph, or maybe none at all. No, it's way higher than this. We've just done a couple of calculations that have said if we let x equal 20 or 25, then y is 1500. If x equals 30, y is 1200. So as I think about what the x values that are important to us are, the x min, I'm thinking maybe 0 to 40, because we've already established the domain of this function. And maybe I should say the implicit domain of this function, given the constraints of the rope and the fact that we want the area to be positive, 0 to 40. So I'm going to press the window button and then set the x min to 0 and the x max to 40. An x scale of, what do you think, 5? 0, 5, 10, 15, 20, 25, 30, 35, 40. Probably appropriate along the x-axis. Along the y-axis, I want it to go up at least to 1,500 square feet. If that's not the maximum value, maybe even higher than that, 2,000 perhaps. So the y min, negative 10 is fine. I'm going to go with 0. Y max, let's say 2,000. And if that's not high enough, we can grab it again a little bit with a little bit higher y max. But I think 2,000 may be high enough. Y scale, you think 100 feet is enough, or would you rather go with something like 250 or 200? What do you think? What would be a good Y scale? I think 100 will work. We'll go with 100. Okay. I think I'll press graph if I've typed this in correctly. So y equals 160x minus 4x squared. I'm going to press graph and see if we get a picture. There we go. Anybody graphing this along with me get a picture that looks kind of like that? Now, numbers on the x-axis represent the values of x. That's how deep, how far into the lake we go. That's our x value. So we've already calculated. I'm just going to do second, calculate, and then number 1 on the list, just to evaluate the function. What we've already seen, second calc 1, what we've already seen is that if x is 25 and we make it 25 by 60, it's going to enclose 1,500 square feet. So you see where that point is on the graph. That's not the highest point on the graph. So I think for a different value of x, we can enclose even more area than that. We also checked it and found that if we make it 30, I'm just going to type in 30. You don't have to do the second calc value again. If you just type in a different value of x, it'll give you a different value of y. X equals 30. That's going to give us 1,200 square feet. But there is a point higher than either one of these. If we do second trace or second calculate, number 4, looking for a relative maximum value, second calculate maximum, and press enter, it'll ask us for a left bound, and then if we give it a left bound, it'll ask us for a right bound. If we give it a right bound, it'll ask us for a guess. Kind of like finding a zero of one of these polynomial functions using the calculator. What we want is to tell it a little bit to the left and then a little bit to the right of this point at the top of the hill. So if I can't tell just by looking at the scale down below, what I'm going to do is press the left arrow until I'm clearly to the left of the point at the top of the hill. It looks like it's about 14 or 15 or so. I could type the number 14 or 15 in, or I could simply press enter and it will use 14.893617 as the left bound. Just like that. Now I'm not sure how far to the right I'm going to have to go. I'm going to press the right arrow a few times. It's about 24. I could type 24 and press enter, or just press enter and it'll use 24.255319 as the right bound. Now for the guess, I almost always just press enter and use whatever the right bound is for the guess. But if you wanted to press the left arrow a few times, so that the cursor gets as close as possible to that point at the top of the hill, that's fine. Use that as the guess, press enter. It'll search and find that the relative maximum there is 20, 1600. 20, 1600. Now, I must have moved to another page there. Yeah, we're on this page. So evidently, if we build this so that it's 20, 20, 20, 20, and 80 feet long, that's a total of 160 feet. It'll enclose 1,600 square feet, and that's the maximum area that can be enclosed. If we just make it 19 feet deep, it's going to be a little bit less area. If we make it 21 feet deep, it's a little bit less area. But if we go 20 by 80, we'll use all 160 feet of the rope, and that's the maximum amount of area that can be enclosed. A equals 20 feet by 80 feet, and that's 1,600 square feet. So we get that from the calculator in this case. Later in the course, when we talk quadratic functions, this is an example of a quadratic function. There is a technique whereby we can actually use a formula to find the coordinates of the vertex of that highest point, and we'll use that in the future to come up with it. All right. Let's see, it was back. This one, any lingering questions about this one? So there was a little bit more left to be done that we didn't quite get finished last time. Let's look at this next homework question. From a 15 centimeter by 15 centimeter piece of cardboard, square corners are cut so that the sides can be folded up to make a box. Complete parts A through C below. So I'll capture enough of this so we'll see the A part. With a large print version there. So the idea is there's a rectangular piece of cardboard, and you cut a little piece, little square corner out of each corner, little square out of each corner, and then fold up the flaps as they were, and you get the box that's pictured there, and the X that you see there represents the height of the box. Basically, you take that flap and you fold it up, and there's the height of X that you get from each of the flaps. How much, I think this is going to be important in determining the volume of this box. If it starts out 15 feet long, and you take away one corner of length X and another corner of length X, how much is left on that side? 15, take away X, take away another X.
15 minus 2x.
15 minus 2x. And it happened down here as well. 15 minus 2x. Those are the lengths of each of these flaps. So if we're looking at our completed box here, it's going to be 15 minus 2x that way and 15 minus 2x that way, and the height of the thing is going to be x. So those are our three dimensions to express the volume of the box of the side x whoa. Okay, so the x is in centimeters. The volume will be in cubic centimeters. It's going to go like this: length times width times the height. We don't want to input that, but we do want to input 15 minus 2x times 15 minus 2x times x. You think MyMathlab is going to be okay with that, or is it going to expect us to multiply all that out? What do you think? Let's find out. (15 minus 2x times 15 minus 2x times x). Check the answer. It liked it. Okay, so factored form is fine. I'd like to believe if you take the time to multiply it all out, it would like that as well, but I'll let you try that. Goodness gracious, the domain of the function. We're going to have to think about this. Might not have to think too hard about it, but we're going to have to think about it. Back to where I can write on this. We start with a 15 by 15 centimeter, 15 centimeter by 15 centimeter piece of cardboard. I suppose if we take away too much, that's what x represents. It's the size of this square that we're going to cut out. If we take away too much, we might not be left with anything at all that we could fold up and turn into a box. So how much, or what's the maximum amount, maximum side length x that we could take away and still have something we could fold up and make a box out of? Or maybe I should ask it like this: what's the minimum amount we could take away and not have anything left? Basically, cut out 4 squares and the entire box is gone. The entire piece of cardboard is gone. So it would look, I know you know what I'm thinking here. We've got this, and if we cut away just a little bit, we might be okay. But what if we cut away this much, and then that much, and then that much, and then the whole thing is gone? What's the value of x? That's the side length of each square that we've cut away.
7.5.
7.5. It's half of the thing. So if x equals 7.5 centimeters, and this is 7.5 centimeters, and all the way around, 7.5s, there's nothing left to form a box out of. So x can't be 7.5 as long as it's less than 7.5, but still positive. If x equals 0, if we don't cut away anything, we're still stuck with the entire piece of cardboard, and there are no flaps that we can fold up if we don't cut away anything. So x can't be 0 because there are no flaps. X can't be 7.5 because the whole cardboard is gone. So in between, I want to say the domain of the volume function is from 0 centimeters to 7.5 centimeters. Anything in between there, and we can make a box out of that. Let's see if it likes that. And if not, let's see what it does like. Does that make sense to me? Let's see. All right, it's good with that. 0 to 7.5. Now it gives us the graph. I'd like to think we could produce that graph on our own if we had to. I'd like to think we could type 15 minus 2x times 15 minus 2x times x. And for our viewing window, x-min of 0 and x-max of 7.5 I think would be appropriate because that's our domain. X-min 0, x-max 7.5, x-scale of 1, because that's not many tick marks between 0 and 7.5 if the x-scale is 1. The y-max, I've got this graph and it's kind of spoiled it. In order to have an idea what the y-max should be, I could do one of two things. I could just press graph and see if the graph is too short and I needed a lower y-max, or if the graph goes up above the top of the screen and need a higher y-max. That'd be the fastest way to make that determination. See, the graph's pretty short, and I've got a lot of wasted space between the top of the screen and the graph, so I'm thinking 2,000, that's way too much. Could I go as low as 200? And then I look at the graph that's given in MyMathlab and think, no, 250 maybe is what I need. So let's go to the window. What if we just did 500? That's probably going to give us a decent graph. Oh, I would just keep from touching the screen there. Okay. So now, part C. Using the graph of the function shown below or one that you can figure out on your own using the graphing calculator, determine the dimensions that yield the maximum volume. Now the x value, I have to be careful here, the x value is, are there 3 dimensions? There are 3 dimensions. The x value is which one? The length, width, or height? So we've drawn the picture. X represents the height. X is it's how long the cutout is. That's how wide each of these flaps is. So x is the height. So let's see what the value of x is. Second calc maximum. I'm going to go with the left bound of about 2 centimeters and a right bound of 4 centimeters and a guess of 3 centimeters. And it looks like 2.5 centimeters. I'm going to say 2.4999989 is close enough to 2.5 to call it 2.5. So 2.5 centimeters is the side length of these little cardboard cutout squares, and it's also the height. So we'll put 2.5 centimeters in for the height. Now for the length and width, we calculate those using 15 minus 2x. 15 minus 2x is what we use to represent the length and the width. So for the C part, 15 minus 2 times 7, oops, 7.5, it's all gone. 2 times 2.5 centimeters, and that's centimeters. So 15 centimeters minus 5 centimeters equals 10 centimeters. I think if we make this 10 centimeters by 10 centimeters by 2.5 centimeters, that's going to be the dimensions of this box. So let's input 10 centimeters there, 10 centimeters there. Is it going to like it? And it does. And it didn't ask us for the volume. That's interesting to me that it didn't ask us for the volume. If it had asked us for the volume, we would have said 250 cubic centimeters is the maximum volume you can get out of a 15 centimeter by 15 centimeter cardboard square, and by cutting out corners and folding up the flaps. That's as much volume as you could get the thing to hold. But that was not part of the question. How do you feel about this one? Any questions about it? Do you see where everything comes from and where it goes? This one is going to involve a little bit of the Pythagorean theorem. This could be a tricky question. MyMathlab may have a fairly decent explanation of what's going on here, but I think it could use some additional explanation. So let's see how this can go. See if that's enough. A rectangle that's x feet wide is inscribed in a circle of radius 7 feet. So inscribed simply means that the 4 vertices of the rectangle actually lie all on the same circle, and this particular circle upon which all 4 vertices lie has a radius of 7 feet. We want to express the area of the rectangle as a function of x. Now you see where the x is drawn there, this dimension right here. So you start with a circle of radius 7 feet. So the circle, if I could draw a decent circle of radius 7 feet, is, oh, certainly not look like that. That's still terrible. But imagine we can inscribe rectangles of various different sizes and shapes in such a circle. We could, and I wonder if I could just borrow this circle right here. I just feel like that's going to be better than whatever circle I may attempt to draw here. There we go. So let's use this circle. I mean, maybe we want our rectangle to have a vertex there, and a vertex there, and a vertex there, and a vertex there, and look like that, and that. It's still inscribed in the circle, so it fits the conditions, and the radius of it, it's the same circle, so it has the same radius length, 7 feet. So you draw a straight line from any of those 4 vertices on the circle to the center of the circle, and that's going to be a measure of 7 feet. Now it's a smaller value of x, as compared to that one right there. So we would expect that maybe the area of this rectangle is different. It's got a different width. It's considerably skinnier than the first rectangle, and it's a little bit longer than the other rectangle. So because it's a good bit skinnier and just a little bit longer, I'm thinking probably it has less total area than the original one. So if we change the value of x, it's reasonable, I think, that we change the amount of area that the rectangle encloses. So the key is, can we express the area of such a rectangle in terms of x? And then if we can do that, we can graph it, we can find the point at the top of the hill, and that'll tell us the value of x we should choose if we want the rectangle to enclose as much area as possible. But it requires the Pythagorean theorem to do that. And the emphasis, the point here is not that the radius is 7 feet. What you really want to see is that the diameter is how long? 14. Diameter is 14 feet. So if you draw the diameter and say the diameter is 14 feet, and you've got x for this other side, immediately you see this is what kind of triangle? A lot of different types of triangles. How would we classify this? What's important to us? It has a right angle, because this is a rectangle, so it's a right triangle. And since it's a right triangle, we can use the Pythagorean theorem, and we can come up with the length of the other side of that right triangle. So this is going to be, if we call this A, and we call this B, and we call this C, and we say a squared plus b squared equals c squared. The unknown here is b. X squared plus b squared equals 14 squared. b squared equals 14 times 14, that's 196, I think. Does that sound right? 196 minus x squared. So b is the square root of 196 minus x squared. And the idea is this. Well, that's a good question, but it turns out we can't take the square root of this and simplify it further to get, for example, 14 minus x. Because if we had well, positive or negative, if we were to square the 14 minus x, we wouldn't get exactly 196 minus x squared, and we wouldn't even if it was positive and we were going for a plus x squared there. We'd get the 196, and we would get a plus x squared. That is right. But we'd also get an x term in the middle. Right, well, if you say you FOIL it, say 14 minus x times 14 minus x, you get the 196, you get the plus x squared, but you get minus 14x, and you get another minus 14x, for a total of minus 28x. So when we take the square of the sum or the square of the difference, when we take the square root of the sum or the square root of the difference, we just kind of have to leave it like that. It's not possible to say this is 14 minus x or 14 plus x. We're stuck with a radical, in other words. Just algebraically, we can't simplify the square root of a sum or difference in a nice way. So put this off in the corner here. Or maybe just delete that. So express the area of the rectangle as a function of x. Well, it's going to be a times b. As we're looking at this, the width of the rectangle times the length of the rectangle. The area equals a times b, the way I've labeled them. So a of x is going to be x, that's what I've indicated as a, times the square root of 196 minus x squared. That's the b, and we get that from the Pythagorean theorem. So if you tell me how wide that rectangle is going to be, and we know the diameter of the circle is 14 feet, that locks us in to a unique length of that rectangle, and we can multiply the length and the width together, and that will give us the area. While we're at it, let's see if MyMathlab likes it. X times, it gives us a square root button, that's good, 196 minus x to the second power. Check it. All right. Let's try to find the domain. What values of x are okay? What values of x are too much? I mean, certainly we don't want x to be 0. Then we don't have a rectangle. Or negative, not 0, not negative. So greater than 0. But how high can it be and still fit inside of this circle? And I suppose we could push the envelope a bit. I wonder if that circle is still on the clipboard. Have I copied anything else since then? Let's do a Control V and see. Maybe right. Ah, there it is. Much easier than having to draw it myself. What if we make it really, I guess, just kind of push it as far as we can push it and draw the rectangle like that? It's not great. You'd think, I mean, I'd struggle to draw a circle, but surely I could draw a rectangle. There we go. So right there and right there. And right there, and right there. About how long is that rectangle? We could go a little longer than that, but not a lot longer than that. What's the value of x here? It's almost 14. Almost 14. It's almost equal to the diameter of that circle. Not quite. Not quite. In fact, if we went, I don't know, with this rectangle, That would be a little bit longer to get to those edges of the circle. If we go all the way to 14, then we have a rectangle. We do not have a rectangle if x equals 14, because that would be the diameter, and it would just be one-dimensional. So I'm thinking it has to be less than 14. It has to be greater than 0. So for the domain, (0 to 14. How do you feel about that? Is that something that is that a conclusion you would reach if you thought about it long enough, or just a little while? Say, yeah, how large can x really be? It can't be 100. It can't be 20. It can't even be 14 because we can't fit a rectangle of length 14 inside a circle of diameter 14. But it could be a little bit less than 14, and would still have a skinny, skinny rectangle. Let's see if MyMathlab likes it. Continue. And it's multiple choice. C. Check it. There we go. Press continue to see more. Graph the function with the graphing calculator. All right, that too is multiple choice. What's that going to look like? Oh, the graphing calculator's being weird. Oh my. That is so weird. So what buttons do I need? I need y equals. So y equals, I believe it was x times the square root of 196 minus x to the second power. And I'm going to close the parentheses. If you have the newer operating system on the calculator, just make sure that the radical extends all the way over the 196 minus x squared. Look at the viewing window. Let's go from 0 to 14, because that's the domain. And I think the x scale of 1 is fine. And our function tells us, the area. I don't think it'll enclose nearly 500 square feet, but I might be wrong about that. Let me press graph and see. So if that's 100, 200, 300, 400, 500, a y max of 200 might be more appropriate. Let's go with the y scale. Let's see, no, not y scale. Y max of 200. And reconsider the graph. So which one does it look like? Gee whiz. Well, either B or C. Either B or C. If I set my Y max at 110, I think that's going to do it for us. So I'm going to set the Y max at 110, and it should look just like answer B. I don't know that I'm all that impressed by the multiple choices that are provided for us, but there we go. I think it's the B part. That's the graph that we would get. Looks like the maximum value is about 100, but it's going to ask us that in a moment. Check it. What dimensions maximize the area of the rectangle? Well, we need the value of x, and if we go to the graphing calculator, we can find the value of x. It's going to be right in here somewhere. It looks like it's about x equals 10, but I don't know. Second, calculate maximum. Left bound of 7 seems like it would work just fine. A right bound of what, 12? Does it look like the highest point on the graph is somewhere in between those two values? For a guess, I'm going to guess 10. I think it might be close to 10. Enter. Well, it's not exactly 10. I don't think 9.899494 is close enough to 10 to call it 10. Depending on how many decimal places it wants, it might be close enough to call it 9.9 or 9.90. I'm going to take that picture and copy it and then see if it gives us any more information on how many decimal places that it wants. Does it, you'd think it would say, right? Does it say how many decimal places? I got to press continue to see more. Okay, fine. Do not round until the final answer, then round to 3 decimal places as needed. Okay. Well, the width of the rectangle, x feet wide. So the width is x. So we're going to go with, 9.899 for the width. Now for the length, I think I'm going to have to calculate the square root of 196 minus 9.8990 something 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 squared. I really think I'm going to have to evaluate that expression to find the length. The other option would be to take the area and divide it by 9.899 something something something. What would you rather do? Two options. Because it looks like the area is right at 98. You could take the area and divide it by 9.8994934, round that off to 3 decimal places, or you could take the expression 196 minus x squared and put the 9.8994934 in for x. I think the first way is better. Let's divide 98 by 9.8994934 and see what we get. And my calculator is just playing games with me here. 98, second quit. Let's get out of that. 98 divided by 9.8994934. I don't need that parenthesis on the end. Whoa! How do we maximize the area of this rectangle? Make it a square. Make it 9.899 by 9.899. And that's how to get the most area out of a rectangle that's inscribed in a circle. So, wow. I don't want to pretend like I didn't already know that, but I really wasn't thinking that way. I was thinking it might be something a little different. I guess I wasn't thinking at all, because that's a fun fact that I learned years ago, that if you want to inscribe a rectangle in a circle and you want to have as much area as possible, do it in such a way that the length and width are equal. Let's check it. There we go. Okay. Questions about this one before we leave it? This is kind of intense. Have the problems we've done to this point been this thought-provoking or brain-numbing? No? That's only 2/3 of the way. Oh, piecewise functions. We've got to talk piecewise functions. But at least it's not a word problem. At least it's not a word problem. So it gives us a piecewise function, so I should back up from this and kind of give an explanation. Piecewise functions, who needs them? What are they? Or maybe, what are they? Who needs them? That type of question first. Then we'll come back to this one. So here we go. This is not a problem from the notes, but it's something I often do, even if I'm just going through the notes rather than working my MATLAB problems. Many real-life applications of piecewise functions. One in particular that I ran across, a natural gas distribution company that I ran across just by doing a kind of a Google search in Canada, gave a breakdown of the procedure they use of calculating their customers' monthly bill. Basically, there are 3 different categories of customers determined by the amount of usage of natural gas during the billing cycle. Now, the natural gas was measured in cubic meters and the bill in dollars, and it's 3 different ways of doing the calculation based on how much natural gas the customer uses in a given billing cycle. So if the customer uses nothing, they've got their gas line turned on. So if they wanted to use any, they could, but it's turned on, but they don't use any gas. Maybe they're away and they had the gas turned off, but it's still active. There is a fixed monthly minimum amount that they get charged. And if they use up to 100 cubic meters of natural gas, they get billed so much per cubic meter, and the graph of that billing function is going to look something like that. If they get billed a little bit more, they get charged a little bit more. There's a fixed amount per cubic meter, and that's the way it would look. And honestly, just for comparison, I'll make it just ever so slightly steeper than that. Sorry about that, but I want to be able to contrast that with the other two. Now, if the customer uses between 100 cubic meters and 200 cubic meters, they still get billed for the first 100 cubic meters, but for each additional cubic meter is not as much because it's a higher volume customer. So if we were to look at how we would go about billing this second customer, or maybe the first customer in a different billing cycle, maybe it's the winter time, and they're just having to do a lot bit more heating, this line segment is not quite as steep as the first line segment, and that just means for the next 100 cubic meters that they use, they're not billed as much per cubic meter. And then finally, for all customers that use more than 200 cubic meters of natural gas, it's a little bit less steep. So I'll begin here and just indicate it looks like that. Now, if we wanted to write this as a function, c of x equals blah, it's not a single straight line. It would be great if we could just say c of x equals mx plus b. And we've got a slope, we've got a y-intercept, and we just input the x value, however many cubic meters that they use. We get that from the meter reader, and then we output the cost. But it's not quite that simple based on the 3 different billing levels. So there have to be 3 different, or one way to do this, I should say, is there can be 3 different algebraic expressions to come up with the bill. Suppose the customer falls between 0 and 100. So I'm going to say if the customer is between 0 and 100, and I'll go ahead and include the 100 in this, cubic meters. How would we do it? Well, we could come up with the equation of the straight line that goes through these 2 points, and that would be y equals a sub 1 x plus b sub 1. I used little subscripts because I want to distinguish them from the slope and y-intercept of the other two that we'll do in a moment. We won't take the time to calculate a sub 1 and b sub 1, but we could if we had to, because we know those 2 points. In practice, we would know the coordinates of those 2 points, or in fact, the value of a sub 1, you can interpret the value of a sub 1, that slope is the additional amount you get charged for each cubic meter, each additional cubic meter that you use. And b sub 1 is the amount that says that it's the fixed cost if you don't use any at all. So we would say a sub 1 x plus b sub 1, and that's how the calculation would be done if x is between 0 and 100. What if x is greater than 100, but less, sorry, wow, I messed that up. What if x is greater than 100, but less than or equal to 200? X is between 100 and 200, not including 100, but possibly including the 200. Well, we would need a different straight line. If you look and extend, if you extend that straight line, it's a different straight line. It has a different slope. The slope is less. And the y-intercept is not really significant for that particular one, but it would have a different y-intercept if we extend that on over to where it crosses the y-axis. So that would be y equals a sub 2x plus b sub 2, a sub 2x plus b sub 2. And if the meter is read and it comes back, the customer used 120 cubic meters of natural gas in that billing cycle, then we take 120 and we would plug it in there in the red X. And that's how we would calculate how much gas, how much they would be charged that month for the gas. And then finally, you've got the heavy users, or maybe it's the same customer, but it's a lot colder in a given month. And so y equals a sub 3x. It's not as steep, a different slope, probably a different y-intercept as well. If the customer uses 210 cubic meters of natural gas, we would take that 210 and we would evaluate this third expression. If 200 is less than or equal to x, and really, I might even say if x is greater than or equal to 200. Because there's no upper bound for that one. That'd be an example of a very useful application of a piecewise defined function. We need different algebraic expressions to define the function for different portions of the domain. So let me go back to the MyMathlab example. There's no application in sight. It just wants to know, can we recognize this as a piecewise function, and can we evaluate it appropriately? And I think we can. For the piecewise function, find the values of g of -3, g of 4, and g of 9. So there are two different portions of the domain. There's the portion where x is less than or equal to 4. So we just think there's all real numbers. I think the domain of this is all real numbers. If x is less than or equal to 4, then we're going to use one rule. And if x is greater than 4, we're going to use the other rule. So when we want to find g of -3, the first question we ask ourselves is this: is -3 less than or equal to 4, or is it greater than 4? Where are we going to find -3 on the number line? Less than or equal to 4, or greater than 4? Yeah, -3 is over here somewhere. So -3 is less than or equal to 4. It's not equal to 4, but it's less than or equal to 4. So we use the top rule. We use the top rule. So g of -3 is -3 plus 5, which is 2. And we ignore the other rule. We don't care 9 minus whatever. We don't need that because -3 is not greater than 4. The fact that -3 is less than or equal to 4 tells us only use that top rule, use the x plus 5. So -3 plus 5, we punch that in, and hopefully MyMathlab likes it. -3 plus 5 equals 2. Check it. And we go to the next one. What is, I don't know what the next one is, I better look. G of 4. What is G of 4? I guess it told us. They're all three right there. G of 4 equals, okay, 4. That's right on the boundary there. Is 4 less than or equal to 4, or is 4 greater than 4? 4 is less than or equal to 4. So, again, we use the top rule. Use the top rule there. G of 4 is 4 plus 5. 4 plus 5 is 9. So we input the 9 and we check it. And it works. And then we do the last one. G of 9 is 9 less than or equal to 4, or is 9 greater than 4? Greater than 4. So that means use the other rule. We don't care about the x plus 5 now, because 9 is greater than 4. We're looking at the 9 minus x. So it's 9 minus 9, which is 0. So we get 0. Yeah, this is not bad. That's a good first impression that they made. That's good. There are other things that we could ask about them that make them seem more difficult, but I'm glad that one made a good first impression. This one's not too much worse. It's got 3 pieces rather than just 2. But I think we can handle this one as well. Maybe I won't take the time to check each of these with MyMathlab, but I think we can do this. H of -8. Into which of the 3 pieces does the -8 fall? Is -8 less than -8? Don't think so. No. Could you say -8 is between -8 and 5, possibly including -8? Sure. It's in the middle piece of the domain here. So for this one, and this one can be a little tricky, H of -8, we're using this rule, because -8 is in the middle interval there. H of -8 is 5. No place to substitute the -8. It's constant on that interval. There'd be a horizontal line segment for that interval. So H of -8 equals 5. H of 1. 1 is also between -8 and 5, yes? So I think H of 1 also equals 5. How about H of 5? 5 is not in the middle interval anymore. 5 is greater than or equal to 5. So just barely in that last one. So how do we find H of 5? We add 4, yes. 5 plus 4. That's 9. And H of 6. 6 plus 4 equals 10. Are we going to get through these piecewise functions unscathed? These next ones are multiple choice. I'm going to let you stare those down and see if you can figure them out. I think I've got some toward the end where it asks you to sketch the graph. Thought it did. The dreaded instructor-created questions, where I've made the questions up myself, and there's no help me solve this. What is the other? Show me an example. There's no show me an example button. There's no help me solve this button. There is an ask my instructor button, but when you do ask my instructor, I'll probably send you a link to this video and say, check this out and see if it doesn't help. So we've got a graph. You have to come up with a function, you're right. The graph is given, and we have to come up with, it really didn't make it any larger, so you have to come up with the function, basically the mx plus b in each case. And really all you have to do, the slopes are nice, and the y-intercepts are fairly nice as well. You could probably stare these down and come up with a y equals mx plus b for each piece. And I think I may just try that for this first one. If we were looking at this ray on the left and wanted to single out a couple of key points on it, certainly the point, that looks like the point -1, 1, and another point just going to the grid appears to be -3, -3. Could we calculate the slope of the straight line passing through those 2 points? We could probably just stare it down and do the rise over run thing, but how about 1 minus -3 over -1 minus -3. Apologize for the kind of the redundant use of the number 1 and the number -3 in this example. But difference in the y's divided by the difference in the x's would be 4 over 2, I think. Does the line look like it has a slope of 2? 2 up, 1 to the right. 2 up, 1 to the right. So the slope is 2. If we went 2 more up and 1 more to the right, I think we would get to the y-intercept. But just in case that's not obvious, y minus 1 equals 2 times x minus -1. Y minus 1 equals 2 times x plus 1. Y minus 1 equals 2x plus 2. So y equals 2x plus 3. This rule can be used to evaluate the function if it's on that piece of the graph, and that's where x, notice it's an open circle, so it goes all the way up to but does not include x equals -1. So this is where x is strictly less than -1. If it were a solid dot, we could include the or equal to bar. But since it's an open circle, x has to be strictly less than -1. So I go ahead and go to MyMathlab and say, okay, 2x plus 3, and the x is less than -1 part is given. I don't have to input that. The other one, I think we can stare it down and come up with the slope and the y-intercept because we're out of time. The y-intercept is -1. The slope is also -1. So -x minus 1. I think that's what it is. Just you could use the point slope form for that, but I think if we check it, it's going to like it. And there we go. Wow, we're probably a section or 2 behind where we need to be. So I'll talk faster next time. But I wanted to go ahead and it's 2.1. There's a lot of substantive problems in that section, and I wanted to take the opportunity to record that video.